Thanks. Thank you very much. So from a human perspective, and a polar bear might draw a different diagram, you can think about the climate problem in a circle somewhat like this. And we have names for all the interventions. So conservation is having less stuff. Efficiency is improving the efficiency with which we produce our stuff, so we then require less energy to produce it. Low carbon energy is finding ways to produce energy with less carbon, whether by wind power, or nuclear power, or what have you. And then the two things which get called geoengineering are finding ways to pull carbon out of the atmosphere once it's already been released. And then the second one, which has now come to be called solar radiation management, although that implies a kind of managerial competence, which in fact we don't have. But those two things together are typically called geoengineering. Then obviously you can adapt to the climate changes once you have them, and you can just suffer the consequences. So that's a way to, sort of taxonomical way to think about what this animal called geoengineering is. And here's a little bit more to tell you about these two completely different things that have almost nothing to do with each other that go under the name geoengineering. So one is a set of ideas that has to do with basically making the atmosphere brighter, so it reflects away more sunlight, which can in some crude way with a bunch of uncertainties and risks, and we don't know much about it, that'll be the subject of my talk, can in some crude way offset or may be able to offset some of the climate risk that comes from CO2 in the air. And there's a bunch of schemes, some of those suggested here. And all of them, and this will be really a centerpiece of my talk, all of them share the characteristics of being fast to implement, of being cheap in ways that can be truly frightening from perspective of global security, and being inherently imperfect and uncertain. And I'll come back to the technical reasons why I think all those three things are true, and then tell you something about the policy implications of those three facts. Now, there are also a bunch of ways to pull CO2 out of the air, a huge host of them, and all of these, I think, more or less share the characteristics of being slow and expensive. And that's because to do this, you actually have to pull billions of tons of CO2 out of the air. And there's no kind of magic trick that allows you to do that in a way that's inherently cheap. Parts of these may or may not be cheaper than cutting emissions, but in a sense, as long as we have positive emissions, a ton not emitted and a ton removed look exactly the same with respect to the global atmosphere. So these things only make sense if they're competitive with cutting emissions, or said another way, it doesn't make sense to think about these instead of cutting emissions because it's just the sum of the two things. Of course, in the long run, these allow you the potential to go backwards in time, if you like, to reduce the actual amount of CO2 in the atmosphere. But that's over a long time scale. And as said, I actually work on one of these with a commercial hat on, direct capture of CO2 from the atmosphere, and I can answer questions about that, but that's quite different and not what I'm talking about this talk. So the idea that you could shield some sunlight is not new at all. This is the first major report to a US president that had all the climate science roughly right, as we now know it. And it was given to President Johnson when I was 2 years old. And it's really worth reading it, and worth reading some of the later reports like National Academy 1977 or the MIT report on man's impact, there wasn't women's, I guess, at that time, on the environment of around 1970, because it is just stunning how early and how much we knew of the basic core story of the climate problem, that if you transport gigatons of carbon from the lithosphere to the active biosphere and do it for a long time, you're going to see pretty dramatic climate changes. What's particularly stunning, if you go back and read this report to Johnson, is it suggests, in fact, one of the few things it actually suggests doing is what we now call effectively versions of solar radiation management. And in fact, there are some Russian reports that suggested it earlier than that. So this isn't new. In fact, there's very little, amazingly little new in the climate science and policy game. I mean, lots of new, wonderful little bits of science, but in the big story, it's kind of stunning how little there is new and how slowly things have moved. For a long time, this topic was not dealt with in the academic literature and policy, and effectively it still isn't. So a big caveat to everything I'm going to say is that there's basically no research, and so a lot of what I'm telling you could be wrong because there haven't been enough people to knock it around. In science, we typically get some sense whether things are really true after we've had a lot of time for different people to kick them around. In the last couple of years, there's suddenly been a big burst of attention, both at Google searches and papers and so on, to geoengineering, and really really mostly the solar kind, and that's what I'll be talking about. But first I want to take a step back and say some things quite similar to what Susan Solomon said about the lifetime of carbon in the atmosphere, but a slightly different twist. So we're all used to seeing these hideous pictures of belching fossil fuel hardware, and it does belch, and of course it actually kills tens of thousands of people in North America alone from air pollution, and that's a low-end number. And it also supplies all these incredible mobility and computation and transportation that is so wonderful for us. But it's a little hard to get a sense of whether the amount of carbon emissions are big or small. There's lots of ways to talk about whether they're big or small, but I have a particular way I like to think about it, which is that this is a geological process on the planet. We are pulling carbon out of the lithosphere and putting it in the active atmosphere and then eventually into the ocean. And so you can say, what's the analogous process? Nature does have an analogous process, and it is seeps and volcanoes. So volcanoes are where carbon is outgassed in the lithosphere, and actually bigger than volcanoes, but a sort of similar magnitude. Oil and gas seep to the surface. Indeed, that's how we used to and still sometimes do find them. And you can add up the size of all those seeps, essentially the natural process that's analogous to the human process of all those mines, and it's at least a factor of sort of 30 times smaller than the human effect. So we are not, a lot of us still have in the back of our minds that we're somehow a small perturbation on the planet. We're not a small perturbation. We're overwhelming the natural process in this case by orders, well over an order of magnitude. That's a kind of conservative view of that number. Picking up on exactly a slide from Susan Solomon's talk, so what she showed you was a slide that's on the right of this. CO2 lasts in the air essentially forever in human times. And one way I particularly like to illustrate that is a lot of us have it in our head that nuclear waste lasts for a very long time, and in some ways it does. But if you look at a reactor waste a year after discharge compared to 1,000 years after discharge, 1,000 years later basically all the fission products are gone. And so the radioactivity is down by, it turns out, about exactly 1,000. So nuclear waste in that sense, and there's different ways to spin these numbers, lasts a much, much shorter time in its really radioactive form than does the imprint of our CO2 emissions on the atmosphere. So it's forever in timescales that matter. Now, another crucial thing to say is that the amount of climate change we get for a given amount of CO2 in the air, as Isaac Held was alluding to, is still deeply uncertain. An enormous amount of scientific progress on our understanding of the atmosphere since 1965, enormous amount since 1979, which was the first date that a kind of official group of people had tried to estimate that range, and they said it was 1.5 degrees to 4.5 degrees C for a doubling. But not much real narrowing of the extent to which we know that number. We know much more, as Isaac Held was saying, about what would happen if it warmed a certain amount, but it's still very hard to say exactly how much it warmed. This is one particular sort of non-scientific take on it that Granger Morgan and I and others have been involved in, which is basically borrowing from basically business and social science some structured ways to ask expert judgments, and these are some expert judgment research we've done, which, reinforces the fact that the uncertainties are large, and in some ways the formal assessment processes, for reasons that are pretty well understood, tend to understate the uncertainties in both directions compared to what they are if you just directly talk to the same people in the assessment process. In any case, you can think about this as spinning a roulette wheel. The MIT roulette wheel is in the upper right. And the point here is that it's the combination of uncertainty and inertia that makes this problem so hard. If we just had the uncertainty but no inertia, it would be sensible to do what a lot of critics say we should do, which is just say, let's wait until we find out how bad the problem is, and then we'll figure out how much we want to pay to fix it. That would be sensible if there was no inertia. But there is this huge inertia, so it's nonsense. And the inertia is even worse than it looks, because there's enormous inertia of the built human infrastructure. So let's say at one point we actually get serious about climate policy, and now that's going to be more my children, because the generation that I've been part of hasn't done much, and the generation before it hasn't done much. After all, arguably we should have been ready to do serious climate policy in the 70s, but we didn't. But anyway, the purpose of climate policy is not to beat people up for emitting carbon or for being bad people because they use energy. These are good things that we want, using energy, or rather the mobility and illumination and computation that it gives us. The objective of climate policy is to, or at least the part dealing with the energy system, is to substitute low emissions infrastructure for the high emissions energy infrastructure. And again, I don't care in this context whether it's wind power or solar power or nuclear power, all the same thing. But these are all expensive, long-lived parts of the energy infrastructure, and it takes a long time to substitute them. So let's say you begin with some sensible policy, a carbon tax with income recycling or cap and trade or whatever you want to do. The purpose of that policy is ultimately to accelerate the buildup of this low emissions infrastructure. But as you gradually build up that infrastructure, the pool of low emissions infrastructure reduces emissions. But the atmosphere doesn't, on a given year, see emissions. The atmosphere sees the buildup of emissions over time, the bathtub analogy that Susan used. And so you have to first build up the pool of low emissions infrastructure, and that's slow because of the long turnover of this equipment. Then you've got to build up the length of time you've had that to actually reduce emissions, and only then do you reduce concentrations. The net effect is it's sort of like driving a supertanker. From the time that you get serious about doing something, and we haven't got there yet, to the time you really notice what you've done, notice that the world is significantly cooler than it would have been if you hadn't had some serious policy, is, you could argue about this, there's no fixed number, but it's something of order a half a century or longer. It's not decades, and that's really crucial to understand. And so we are making decisions every day by not having any climate policy that are decisions that commit us to having more carbon in the atmosphere and therefore carry on costs to our children and grandchildren that are very hard to reverse. So I'm going to talk about this scheme called solar radiation management, which has in some respects the ability to partially reverse it, and a lot of the moral and practical concerns about talking about this technology come exactly from the fact that it might encourage people not to reduce emissions. So let me start with some real basics, and I'm going to keep most of the science out of this core of it. There's no question that if you add reflected particles to the upper atmosphere, you will cool the planet on average. And if you could choose how much reflective particles you add to the upper atmosphere, if you warm up the planet with CO2 and then cool it back down by increasing its reflectivity, you could certainly bring the global average surface temperature back down to some level that you wanted. But if you did that, you certainly would not have the same climate. For reasons that are, some of them, very, very simple to understand. There's some simple arguments you can make about where radiation balances in the atmosphere. Essentially, there's a thing that we think of as the radiation layer, maybe 5 or 8 kilometers over our head, which is the place where outgoing radiation to space has to balance the incoming shortwave radiation. And because of the way that works, it turns out that if you brought the global average surface temperature back to the same thing after increasing it with CO2, you would certainly have a weaker hydrological cycle, less evaporation and less precipitation. Not necessarily less soil moisture, but different, and that's the kind of stuff Isaac Held could answer well. What is clear is that it's fast. So this, what's been up on the screen here was Mount Pinatubo, which the actual smoggy, or not smog, but the actual dust that you're seeing there is not the thing causing the climate effect. It's the sulfur that gets into the stratosphere as SO2 and then oxidizes to H2SO4, sulfuric acid, and forms little droplets. That is the thing that actually has the climate impact. And in this case, something of order 8 million tons of it went into the stratosphere, and you saw cooling with a timescale of about a year. So how imperfect is it? I'm going to show you a bunch of slides that illustrate that it may not, in functional terms, be as imperfect as you think. But by it, I mean solar radiation management. But this is just one study, and there are lots of ways that it may still be very imperfect, and this study may be wrong. But I just want to give you some sense of this. What this shows you is for a range of places. These are often in hydrology literature or impacts literature called the Georgie regions. There are some standard regions that have coherent variability of temperature and precipitation, so 20-some regions. And we have looked with a standard model, the Hadley model, at the temperature and precipitation changes under a temperature increase scenario, and then looked what happens when we add various amounts of aerosol to the upper atmosphere in this model, not obviously in reality. And the units here, by the way, are not degrees centigrade. The units are relative to interannual variability, which is a useful proxy for thinking about impacts, because in many ways, impacts scale as how far away you are from the interannual variability. So the way to read this graph is for the temperature side, the blue line, well, for both sides, the blue lines are what happens if you do CO2 alone. And so for temperature, you can see that it pretty much gets warmer everywhere. And so if you look at Eastern Africa, the very bottom one there, it gets a little more than 2 times the previous interannual variability warmer. And for precip, you can look. And then if you add a certain amount of solar radiation management, you can bring things back towards the pre-industrial. But the question is, how unequal is it? How to think about the winners and losers, and how to do that in a quantitative way. So now I'll come back to this slide, but I'm going to take you through a sort of simplified, linear way to think about the trade-offs between winners and losers. So let's say you have 2 regions. And I'll start with just calling them region A and B, but you might think about some political implications of these regions being real countries. So if you increase the amount of CO2 in the atmosphere, you're going to warm region A and region B, or change the precipitation, not the same thing, but this model could be used that way. You're going to warm them up, but not equally. If you add sulfate aerosols to the upper atmosphere, you're going to cool them, but not equally and not in the same way. So when you add the two things together, they won't compensate exactly, because the two effects are just different. The climate effect of adding CO2 and the climate effect of adding sulfur aerosols are different. And so you can imagine something like this, and you can imagine, let's say, that you want to adjust the amount of solar radiation management that you're doing, and so this adjusts it so that it's just right for region B, but region A is too warm, and if region A is in charge, maybe, if region A is in charge, I can flip these around. Anyway, I think I missed a slide there, but you can imagine some optimal compromise between the two in principle. And the real question, a simple way to ask the question of how unequal geoengineering is to say, what is the angle between this vector for the CO2-driven climate change and the vector for the solar radiation management? I just drew these pictures. Maybe it looks more like this, in which case this is really quite useless, because any amount of this SRM actually makes things worse for region A. So we did this in a simple model. We actually did this in 22-dimensional space, these 22 regions, and we can do it for temperature and precipitation, and we can actually look at what that angle is. Now you got to decide how you weight the regions. And so we said, well, we could weight them by money, or by people, or by land, sort of thinking of land as being a proxy for total impact on the natural world. And the answer is the angle is amazingly small in this model. So, for example, weighting the temperature vectors by any of those things, you get angles of a few degrees. And what that means is the compensation in this model appears to be remarkably good. Or to say it this way, let's say that you were in charge of adjusting the amount of solar radiation management, so you were going to minimize the overall deviation in precipitation across all these regions on a population-weighted basis as much as you could. So your job was to minimize the change from pre-industrial precipitation across all the people in the world, more or less. If you did that alone, not thinking about temperature, you'd still actually eliminate 70% of the temperature changes on the same basis, it turns out. Or rather, no, on an income-weighted basis. I just sort of picked that one out of the air. There's lots of combinations like that you could pick. So this was quite a surprising result, because people have made very strong statements about how stunningly unequal this is, and we just kind of went ahead and did the obvious climate impacts thing and found that it didn't look very unequal. And that says something about people's preconceptions about what the answer is here, and I'll say a little bit more about where those preconceptions come from and why. Now, there's lots of caveats. This is one climate model. We don't have a real impacts model. We can try in this toy thing taking the square of delta T and the square of delta P, the change in temperature and precip, but it's not clear it means much. People are doing more, though. Some other colleagues who I work with, Ken Caldera's group, have actually now used a full crop impact model, and this is the crop impact model that comes from David Lobel and colleagues, and it has its own problems, and not all these crop impact models are the same, but this is one of the leading crop impact models. And so we've looked using climate models driven either with or without geoengineering at what the crop impacts are, and the results are, in a sense, not surprising, but there is a pretty disturbing thing in here, which I'll come back to in the end, about what people might want in the long run. So what you have on the, I don't know if it's a pointer here. Try the pointer, well, whatever. What you have on the, what you're seeing is the right-hand side is these models when we try them without CO2 fertilization. On the left-hand side, when they are with CO2 fertilization. Little red button here is just barely doing it. I don't know, I can barely see it. Anyway, and the top lines are what we get with increased CO2 but no geoengineering. So the way to read this is for a bunch of regions and for a bunch of individual crops, this is increase in crop productivity and decrease under a regular climate change scenario. And this is the work that these groups do sort of for a living. And the main thing you see, which you might not be surprised about, but is exactly one of the fundamental big impacts of climate change, is you see a big dispersion. There are winners and losers. And that's one of the serious reasons to be concerned about climate change. Forget about geoengineering. And what you see when you do geoengineering in this simple model, which might be wrong, is in one of these variants, the variants with no CO2 fertilization, it brings everything back pretty close to where it was, leaving a slight increase in overall productivity. If you put the CO2 fertilization amount in, and there's basically two variants of the models that do or don't count it, and it's not clear where reality lies in between those, you find that crop productivity is up almost everywhere. And that is simply because for many crops, they're going to do better in a high CO2 world with with about the same temperature, but they don't do well with temperature extremes. So now a little interlude on the engineering, and then I want to really come back and talk about what the implications of some of this are, because the implications are big, and some of them are really quite frightening. So there, as I said, been very, very little serious work done in this topic, and people have pretty much all assumed that you would copy volcanoes, as I said. And so the assumption has been that you'd put in SO2 in the stratosphere the way volcanoes do, and that appears not to work very well. And the reason is that the effectiveness of these little particles in scattering sunlight depends very, very strongly on how big they are. If they're bigger than, say, half a micron, they don't work very well. They don't work very well both because of the physics of scattering, something called Mie scattering, and also because they get too heavy and they fall out of the stratosphere too quickly. And if you just put SO2 in the stratosphere, SO2 actually itself doesn't ever make particles. It has to turn into H2SO4, which is a condensable gas, before it makes particles in the part of the stratosphere we care about. And when you do that conversion slowly, the H2SO4 kind of appears everywhere and ends up almost all of it going into new particles eventually. And the result is that as you add more and more sulfur, you go down a curve like this. This is the amount of sulfur you're adding per year, between 0 and 20 million tons a year, which is a gigantic amount. That's 2 pentatubos a year, roughly. And this is the radiative forcing in watts per square meter. And you see, if you just do this the way people have talked about doing it, there's different models we have of how it works, it hardly works at all. It's what we call asymptotes. You have to put in an absurd amount of sulfur, and you get quite a small amount of radiative forcing because you keep making these big particles, and they keep falling out, and they're not very effective. So we thought about how we could actually do this better, and we realized that it would make a lot more sense if you control the particle size, and the way to do that is to release the sulfuric acid directly from an aircraft, and then you can easily tune up the plume coagulation in those aircraft plumes to make particles of a range of sizes you can control pretty well. And the person who did this, Jeff Pierce, is a aerosol nucleation expert who I brought along with the people who are the atmospheric chemistry experts. And the bottom line is, if you do this scheme, you can make things go like this, which is what all the previous papers in geoengineering had all assumed this, but it's not true with SO2, but it would be true perhaps if you did this scheme. This is a single paper. This one really might be wrong. I mean, people haven't had time to think about it very much. But nonetheless, the result is pretty dramatic. The result is that this idea that people talked about forever appears more or less not to work. And there are relatively easy technical ways that might make it work a lot better. And once you start deciding you want to be a technologist and play with your toys, you can keep thinking of better and better ways to do this that might actually be better in the sense of having less environmental side effects. So you can think about using things other than SO2 that might have less effect on ozone loss or other things, and I'll just mention a few of them. I should say that actually in this particular model, the ozone loss gets a little bit worse because you end up making more surface area. There are really wild ideas. I'm just going to touch on this. This is a paper I did about how you could actually make levitated particles. This is actually 19th century physics. It's nothing as fancy as it sounds, but in principle you could do this, and there's some reason to believe that the cost might not be absurd. And with these particles you could get away from a bunch of the problems people have been concerned about. You could have them over the stratosphere and so not have them directly contribute to ozone loss, so there may be indirect ways that would make the ozone loss problem better or worse. And you could also perhaps make them congregate at the poles, where you could concentrate the reflection where you might want to concentrate it most, where the amplification of global warming is the largest at the poles because of the ice albedo feedback. It's a fun example, and what it really shows you is the following. I'll say we've also looked at the costs of doing this, and I just want to confirm the costs are absurdly low. And it's easy to get excited about this, and people who like technology will argue about whether the cost should be exactly here or here, but these are costs of order $1 billion a year to alter the Earth's climate, and in a $55 trillion economy, that's effectively zero, and that's not necessarily a good thing at all, as I'll come back to. There's some really frightening things about those low costs. But this was a study by Aurora Flight Scientists that really, Science is a consulting company that really did or aircraft engineering company that did a pretty careful job looking at a range of approaches to get 1 million tons a year to the stratosphere. This is the end of the little detour on technology. The most important things to say is it is much easier to think of new, clever tricks that might plausibly actually give us better ways to manipulate the Earth's climate in a way that could actually protect our environment. It's much easier to think of those ways than to understand their effectiveness or environmental risks. And I think that's going to keep happening. So as this sort of cork gets pulled out of the bottle and people publish more and more papers, there will be many, many more papers with more ideas, some which might genuinely be useful or potentially useful and potentially give us this high leverage way to cut environmental risk. But understanding how well they really work is much, much harder than just cooking up some new ideas. There's an enormous scope for new methods. So, I and a couple of collaborators had now thought of several new methods that nobody thought of that really appear to be quite different, and we found that the original method didn't even work very well. And that's a quite small amount of work, and the only reason we're able to do that is not that we're particularly good at this, but that nobody else has been bothering to do it. It's going to be impossible to really develop certainty about the details of how well these work and their environmental effects without some level of process testing. I mean, there's enormous history in environmental science that shows you that pure laboratory computer work can miss big, big parts of the real world. So now I want to sort of finish the main technical part of what I want to say about geoengineering. Now I want to come back to linking this to policy in various ways. So I want to review the three things I said. One is that it's fast. That we know from basic physics. We know it from Pinatubo. There's no question. Two is that it's cheap. And I mean, in saying that it was cheap before, I said, oh, well, we've done this study from an aircraft engineering company. Well, don't believe me because of one study. The underlying reasons why it's cheap, I think, is robust, and it really has to do with pretty basic physics of scattering. It just doesn't take very much material in the upper atmosphere to do the scattering. You only have to lift sort of twice my mass to the stratosphere every second in suitable small submicron particles to offset the raw radiative forcing of 2 times CO2. Obviously not to completely reset the climate. I'm not claiming that. In fact, I know it's not true. But that gives you a sense of the frightening leverage we have. So this is another example, and I'll come back to analogies to nuclear weapons and other unpleasant things. The analogy is to other ways in which science has granted us extraordinary leverage over the planet with powerful implications for good or ill. But the bottom line is cost is not going to drive decisions about implementation one way or the other. And despite my little story about this interesting work we've done that shows it might be not as imperfect as a lot of my colleagues think, there's no question it's still imperfect. This is not a direct compensation for CO2 in the atmosphere. For one thing, it does nothing about the geochemical impacts of CO2. For example, CO2 will acidify the ocean and will remove many of the coral reefs that we love over the next century. So let's now think a little bit about policy implications. So the fact that it's cheap and it has high leverage, and I'll come back to what I mean about that in a second, means that decisions about implementation will basically are risk-to-risk decisions. There'll be risks of doing it and risks of not doing it, but they will not be benefit-cost. And it means that very differently from the choices that we face in getting nations of the world to cut emissions, where the issue is getting many nations, not all of them, to share a common burden, an individual cost that has a future shared global benefit. In this case, the challenge may be to control the action of rogues. Obviously, I'm not claiming that other states are rogues and we're not, but any one state is a rogue if the other ones think it is, in a sense. But the point is that this is so cheap that any nation in the world could do it. They could hire the technical ability to do it. And you can think of all sorts of scenarios. You can think of the small island nations who have been very vocal in the climate negotiations so far, saying, we've hired Lockheed Martin to build the equipment, and we are going to start doing this in 2025 unless you guys get serious about cutting emissions, for example. The fact that it's fast has several implications, but one of them is it allows us to deal in a partial way with this uncertainty and inertia problem. One of the core problems of the climate sort of challenges of managing climate policy is we don't know how bad the problem is, but if our only tool is cutting emissions, we really don't know how much to cut, because if it turns out that the climate problem is very bad, if we are unlucky and the climate sensitivity is, say, 5 degrees C for a doubling, then it could be that the amount of CO2 that we already have in the air, or will very soon, is really unacceptable in many respects for future emissions. And there's no way to go backwards except for these geoengineering technologies. So when you think about this without these technologies, it's hard to know how to manage the risk. And this is essentially a risk hedging technology. And so one way to frame these technologies is to say we would only use them if it turns out the climate problem is much worse than we think. Finally, the fact that they're imperfect means that these cannot ever be a perfect substitute for cutting emissions. So if you say, and many people are tempted to say, oh, this is so cheap, let's just do this and forget about cutting emissions, That is not a strategy that will keep the world safe from climate change, because if you really did that and just kept increasing emissions and therefore increasing concentrations, you would walk, and at the same time increase the amount of reflected particles in the stratosphere, you would walk further and further away from the current climate state with increasing risk, unbounded increasing risk. It might be safer than increasing emissions without SRM, but it would not be safe. So let me, last part of the talk a little bit about what my fears are here. And I'm actually only going to, at the end, come to the most obvious fear in a sense, which is that this may not work very well and that there are a bunch of technical problems, because I'm sure there are. But actually, a bunch of my fears are about the interaction of this high leverage technology and the human system. So introducing something that is high leverage, that means cheap, easy to do, fast acting, and unequal into a world that's a multipolar, tightly coupled, unstable world increases the likelihood of conflict, or it could. I've referred to high leverage and low leverage earlier in this talk. Here's a way to think about this across things that have nothing to do with geoengineering. So high leverage technologies are technologies where we tend to make risk-to-risk decisions, where money isn't the central thing that plays a role in implementation. So, for high leverage things, you could think about nuclear weapons or malaria vaccine or germline genetic engineering, et cetera. And these are geoengineering ones here. And for low leverage things that have completely transformed the world, you could think about passenger air transport or public water and sanitation, as Rita Colwell was talking about. These are things with enormous leverage. Maybe actually Rita's strainers count as high leverage, high impact things. But in general, building public water systems are not too cheap to meter. It costs real money to do them. The benefits are gigantic. Conventional weapons, you might say, are in that category. So I would say that SRM, solar radiation management, fits in this kind of high leverage category. And CDR, carbon dioxide removal, fits in the low leverage category. It's something that may, or some elements of carbon removal may be useful, but they're inherently expensive. They don't give you these kind of arbitrary powers. There's no danger that Dr. Evil is going to suddenly suck all the CO2 out of the air because it's just inherently too expensive. There is, in some sense, a danger that a Dr. Evil will decide to mess with the climate through SRM because it is so cheap. It's theoretically possible. The second sort of fundamental concern I have is really, you might call it accelerating the end of nature. So I hinted about this in the stuff I said about crop productivity. It may well be true that if your job was to maximize global crop productivity or maximize the carrying capacity of the planet purely for people, it may be true that you would actually prefer a world with more like 1,000 ppm, and then you'd engineer the climate back to some climate that was optimal for growing crops. That is not what I want personally, but it may be true. And when we invent technologies for one purpose, people are free to use them for other purposes later. Humans tend to use the tools that they have to shape the environment to their will. This is not a new idea. In the end of the 1982 National Academy Report on Climate, one of the ones that really helped to start the whole modern focus on climate change, I now know it was Tom Schelling because I've asked him. Tom Schelling wrote, "Interest in CO2 may generate or reinforce a lasting interest in national or international means of climate and weather modification, and once generated, that interest may flourish independent of whatever is done about CO2." And I think that's precisely my concern, that as that these technologies, which certainly I personally and many of the people I work with are conceiving as things that might be a hedging strategy to minimize the risk of climate change, with my personal view, but this is a value statement, not a science statement. My value statement is I would prefer that we try and use these technologies and cut emissions in order to keep the world more the way it was for the natural world. That's a value statement. That's not a scientific statement. But I am aware of the fact that future humans may look at this differently, and that going down this road may go down a road of really engineering the world in ways that will have really profound implications. I think you can't understate them. So the last one, obviously, is this, or the second last one, is this sort of easy out moral hazard that I've hinted at but haven't quite said. So, I don't spend all my time working on geoengineering. In fact, integrated over my career, a pretty small amount of it. And when I go into policymakers and urge them to think about working on climate, restraining emissions, I say that I talk about these high consequence, low probability events, and I say, well, these are reasons why we should have some insurance policy and cut emissions. So, and so do many of my colleagues. But knowledge that geoengineering is possible, which is, I think, emerging, makes these climate impacts at some level look less fearsome and makes a weaker commitment to cutting emissions now, or might. And that is the underlying fear that I think I've actually coined the term moral hazard in this debate, but it's the wrong term. might be more like overconfidence in technology leading to more free riding on our grandkids might be a better term for it. Of course, the other reaction could happen. It's not certain what will happen. This little cartoon actually says much more accurately what the underlying issue is here. If you can't read the bottom ones, the little guy at the bottom says, "We'd better hurry." But the real punchline is always these Tom Tolles cartoons. The other little guy at the bottom who says, no, that's the great thing about this technology. We don't have to hurry. And that's exactly the worry, is that, and it's also the promise. At some level, these geoengineering technologies do allow us to have a partial, imperfect time machine, in the sense that as we go forward in time right now, we're building up carbon in the atmosphere, and in principle, some combination of these solar radiation technologies and removing carbon allow us to go backwards a little bit, however imperfectly. But the consequence is exactly the consequence in this cartoon. Finally, of course, there's a bunch of side effects and risks, which I don't mean to minimize at all, but I personally actually think the things to do with the interaction of the human system and the natural system are likely to be more serious. Thank you very much.
My impression was that we tried to get some form of sulfates out of the atmosphere 30 years ago. For whatever reason, I have no idea. Are they the same type of sulfates, and is there a health risk in putting them back in, or is it a question of what part of the atmosphere?
It's a good question. And you might also wonder, and people do, about acid rain risk. The answer is that first of all, my guess is when you get serious about doing this, you will quickly end up not doing sulfates because there are better things to do. But if you did sulfates, in order to compensate for, say, a watt per square meter, which is the most, I think, in any foreseeable future that's you're likely to do, it's a little strong, you're talking about something like 1 million tons a year. And we right now put 50 million tons a year of sulfates in, roughly. And the places where those are really killing people from air pollution, as Paul Epstein can tell you much better than me, are really in places that it's concentrated. And so I think there's a lot that might be wrong with this, but there is essentially no impact of these on tropospheric air pollution, and also no impact on the global acidity. And in fact, people have done calculations that show that's not true. Lots that might be wrong. I think the health impacts are not likely to be directly from the particles, but if the particles end up accelerating ozone loss. And in the standard models, they don't do it very much, but as my colleague Jim Anderson points out, there are scenarios under which the stratosphere gets wetter where you could end up having substantially greater ozone loss with particles in the stratosphere. So that would be a health impact route.
Thank you for your talk, Dr. Keith. I have a bunch of things to say, but to follow up with that last one about the acidity, the acid rain and so on.
Yep.
If you're actually going to be concentrating most of the aerosols in the polar regions, then the polar regions will be more affected by acid rain, and that even though no people live there, polar bears and all the other marine life do live there. And I remember one of your slides actually said one strategy is to continue targeting the polar regions year-round, and that means that in the winter seasons, definitely the ozone layer will be even more destroyed because of the critical temperature reached. But in general, I want to comment that even though in your talk you repeatedly mentioned about the risk and so on, but I find that just similar to this entire body of literature, authors and speakers generally, even though they will say things about, well, we need to keep in mind about the risk, but they never seem to fail to promote the method as a way of substitution, even though it may be an imperfect or partial substitution. But even you use the word substitution in there, and also a time machine, phrases like that. I think it's extremely dangerous. For example, so I have a bunch of things, and you may cut me short because there's not enough time.
It makes sense for you to talk a bit.
Right, okay. So certainly it doesn't remove CO2. So engineering types of scientists generally don't think of the effect on the biosphere or biomes, but it doesn't help if you decrease the temperature a little bit from what would have been caused by the CO2 if the concentration of CO2 is still there. For example, the stomata size of plants is still going to be constricted, and also you might greatly...
Can I interrupt? So maybe what you meant to say was it doesn't fix the problem. So
yes,
saying
yes.
that doesn't help strikes
different.
me... Can I speak for a second? saying that it doesn't help strikes me as a kind of overconfident statement. I think you really have to do the work. I am not advocating that we do this.
Right.
I'm advocating that ignorance is dangerous on both sides. So you just said confidently that it wouldn't help. And I would say that the evidence so far is that it would help in some ways and hurt in others, and that it might be useful to know those ways better.
It's actually tinkering with a system where
We're going to move on to other questions, and at the end of the day, there's going to be a reception, and you're welcome to ask specific questions.
But let me just say on a personal note that I travel in the high Arctic quite a lot. I actually had my first job in science working on polar bears. And I think that I take this seriously precisely because I think that it's very unlikely or impossible that humans working on their own for their own benefit will do very much to prevent the warming in the Arctic.
yes, but I think that many of the research, the promotions really indeed is much more human-centric than biocentric. And the
that may be true,
phytoplanktons,
but
for
I'm just
example,
speaking for
will be
myself.
severely affected, I think.
Hi, Professor. Thanks for your talk.
Yeah.
The question I had was, the recent events in Japan highlight the fact that when we're dealing with high-risk technologies, safety systems work until they don't.
Mm-hmm.
So I was wondering if the events in Japan have an effect on the public debate or even the academic debate about geoengineering.
It's too early to say. I do think the events in Japan serve as a good reminder of the way that safety systems, that engineered systems tend to fail in unpredictable ways because of the interaction of the human decisions and the built system. I think that will certainly be true here. In a sense, that's exactly what I'm saying. To me, the worst failure modes for geoengineering are probably precisely that interaction between the technology and people. So let's say the Chinese government is concerned about losing crop productivity, and that's because their monsoon is weakening. There's some real evidence the Chinese government is now concerned that way. And they decide that by whitening, using these cloud whitening techniques, the ocean off the Chinese coast, they would increase the monsoon, because monsoon has to do with the land-sea contrast. Whether or not that's actually true is at this point irrelevant. Let's say they decide to do that, and the Indians believe that it's going to do the opposite. So these are both nuclear-armed states. We have no way to resolve that conflict. And to me, those are some of the most likely ways that this is going to be unpleasant. I mean, I didn't invent this idea. What I think is that we will be more at risk if we do nothing to learn about the risks and benefits here and blunder into it. That would be worse than knowing. And I actually think if we have a research program, a limited research program, we'll keep finding more problems with geoengineering, and I think that's a good thing.
So I wanted to comment on your statement that the end of nature to you is just kind of avoiding that as a personal preference. As somebody who works, I'm an environmental chemist, and I'm someone who tries to understand the natural processes that keep this planet habitable. And as somebody who does that, I know that we are so far from understanding those processes that we absolutely depend on, that the end of nature to me represents a tremendous risk. We don't even know how big a risk it is, but I would put it under your risks, not as a personal preference to avoid.
You may be right. I hope you're right.
Is there a way that solar radiation management could be used on a local basis?
Generally not. The Earth's climate, there's obviously a history of attempts at weather control, most of which don't work very well. And a natural question you might ask is, how the heck can you think you could achieve any measure of climate control when people haven't achieved weather control? And that question actually has an answer that's analogous to the question of, how do you scientists think you can predict anything about the climate when you can't predict the weather a month in advance? And they're related pieces of physics in the same directions. In some ways, it's actually easier to manipulate the climate than it is to manipulate the weather.
Well, let me ask it another way. If I were to learn that I could use solar radiation management to lower the temperature in my country or in my region,
I think it's close to impossible to do that because winds couple temperature together. And so when people have done some playing with this, and when you say try and just cool the area north of 60, you see cooling of the whole
I
world.
didn't say just.
Okay.
What my thought is that somebody would try to do this for their area without care for the spillover effects.
Yes, that's,
So that as the particles distributed,
Yeah.
thanks. As the particles distributed and the impact wore off, you just take your airplane back up and spray more particles around and keep your area cool without concern for what happens in the rest of the world. And so,
I think exactly the risk I'm talking about
Okay,
is
good.
the risk that
Yeah.
countries would try and act unilaterally, and given the inequalities, they could be real. But what I'm saying is your chance of kind of locally cooling your small country is more or less the physics of climate says that that's not doable.
Okay. So now that I understand it better, then I'm very concerned because I think history shows that we haven't developed a technology that somebody could benefit from that hasn't been put into effect.
Well, I think there's also room for optimism. We have developed nuclear weapons, and through a combination of luck and real wisdom on both sides, we have steered our way clear so far. And we've actually, in the consequence of doing that, developed quite strong norms of international governance that have arisen partly because we had that. And I think one way to say it is that solving the climate problem, either by cutting emissions or by developing or actually doing this, requires a kind of global governance that we don't have right now. And we simply have to develop it. I don't mean some black helicopter single UN thing, but we need the capacity to govern the globe for lots of reasons, and this is one.
So I assume you would say then let's get busy developing that mechanism.
That's just to say, absolutely. Indeed, we just ran a meeting 2 weeks ago in London that was the Global Solar Radiation Management Governance Initiative run by Royal Society and Environmental Defense, and that brought some people from around the world to talk about how we might govern this from a range of different countries and backgrounds.
Thank you very much.
Thank you.